Hi, it's time for another math easy solution. Time to discuss further into applications of integrals and look further into moments and centers of mass. And now look at the case where we have the region is bounded by two curves as opposed to the curve on the x-axis. Basically, in my earlier video, I derived the formulas for centers of mass for a region bounded by a function and the x-axis, such as this one here. So this is a recap of the earlier video. So if we had a function like this, which is y equals f of x, and the region underneath, and we're trying to find the centroid or the center of mass, which is looks something like this, where the coordinates are x and y like this. And again, the region is bounded by this x-axis and this curve above there. And the formulas I derived were these right here, which were x equals 1 over a times by integral from a to b of x f of x dx, and for the y coordinate of the center of mass is equal to 1 over a times integral from a to b of 1/2 times f of x squared dx, where a is the area of the region, and you could write that as integral from a to b of f of x dx. And in fact, we could use the same sort of argument that led to the above formulas, but this time to obtain the formulas for the centroid or center of mass of a region R that lies between the two curves y equals f of x and y equals g of x, where f of x is greater than g of x. And doing so, we'll obtain the following formulas. Basically, what I'm going to do is solve this using this pretty much the same derivation that I used to get these. So make sure to watch that video to get it in a bit more detail. And basically, the idea is, if we were to, let's just graph this out. This is the x y axis. So now we have two curves. So we'll graph it like this. This is, this curve right here is the y equals f of x. And then let's say this curve below it is the g of x, y equals g of x. And now you have two curves, and the region we are evaluating is this, of trying to find the centroid. Centroid from this looks probably somewhere like here, roughly, just by symmetry. This is like that. And this point is that. And this is our centroid C, which has coordinates like that. Yeah, and this whole thing is our region R, and this is from A to B are the intervals that we are trying to determine the centroid. And now basically we're going to follow the same exact argument which was before. Break this up into infinite number of rectangles, but first let's just take one of these rectangles at this point, and I'll just draw this, we'll call this x, center line I for just any ith rectangle, and we're going to draw a rectangle across this point. So now we have a rectangle. If this is the region R, this sub-region, we'll call it Ri. So that's the subinterval, and they all have a width of delta x. This is going to be our delta x. And now we could, we know the distance from here at this very point right here is just this point, which is, this is our g of x center line like that. And then this top one all the way down is going to be, I'll draw this all the way like that. That is just this point, which is f of x. Alright, so it's a point on the top curve, this one's a point on the bottom curve. And now this length across, we'll just call this hi, just to make it neater right now. And then the center of this, basically like I showed before, the centroid of this rectangle is the exact center of this rectangle by symmetry. So then this point all the way across here, we'll call this yi center. So this is the center of mass of this sub-region right here. And again, when we approximate and make an infinite rectangle, sum it up, we'll get this exact one here. And then again, this point from here to here by symmetry is hi over 2, so it's half the distance. So what do we end up getting? Let's just derive this yi first. So this center line of this subinterval or this subregion is going to be basically this length plus half of this full length there. So g of x I like that plus hi over 2. And now this hi, that's just a difference between the top distance minus its g of x. So that just simply equals 2, like that, plus f of x minus g of x, all divided by 2. And now just use common denominator times by 2 over 2, and then we get this 2g of x I minus g of x, that's 1, so that's positive g of x. So we have f of x I plus g of x I over 2. So this can be considered as the average distance. And again, yeah, that's just the average distance up to here. So the average value of this top curve and the bottom curve. And again, the next step that we used in our earlier video in deriving these formulas is first we get the moments. So the moments about the y-axis, let's just draw this, yeah, moments about the y-axis, so to get to this one, it's going to be, well, again, the limit as n approaches infinity, because we have infinite sub-rectangles, so I equals 1 up to n of mi, and I mean moment about the y-axis, ri. So we have infinite number of regions. So what we're doing is taking the limit as we sum up these to infinite number of regions of the moments. And now this ri, basically exact same what we did in our last video. And now to solve for this mri, so for any random sub-rectangle or subinterval, the moment about the y-axis, this equals 2, like I explained. So if it's a moment about the y-axis, a tendency to rotate about this axis, and that is basically going to be the mass times it by the center of mass here. So up to this point, xi, like that. And this one here has a mass mi. And again, like I explained before, the moment, this one is going to be mi times it by x center of mass point, like that. And this equals 2. If this has a constant density, so let's just say it's constant density. No, so the mass is just the constant density times by the area of that region. Again, like I explained in the last video. So, and then we multiply this by this again. And now this area of this region, well, the area of this rectangle is simply hi times delta x. So, yeah, that's just the area of the height times width of the rectangle. So this equals to rho, and let's just get the area. Area is going to be delta x times it by, let's put this like this, times it by, this was the hi, or simply f of x I minus g of x I, like that, times by xi. So that's the area. So that is the area point, like that. And now we just simplify this further. Yeah, and then we end up getting rho xi and then f of x I, like that, minus g of x I. So that's what our subregion is right here. And now what we do is just plug this into this limit, so we get an integral. So what we end up getting is total of moment is going to be limit as n approaches infinity of the summation I equals 1 up to n rho xi, oh, in front of delta x right there, so the delta x goes there. So f of x I minus g of x I delta x, and then this is, again, this is by definition Riemann sum, which we could write as an integral. So this just equals 2, and take this as a constant. Let's take it out. So integral from the whole region, so a to b of, and now this xi, when we're taking infinitely small subsection of the delta x, this xi is pretty much going to be, it's going to coincide with this point here, which is xi, and this is xi minus 1. So it's going to coincide, and we're going to call it just x, because it's super, super small. So x, and then this is all f of x. Put this bracket minus g of x, and then dx for infinitely small delta x. So that's what our moment about the y-axis is. And now let's get the moment about the x-axis. So this equals 2. Again, it's going to be the same thing, same idea. You take the limit as n approaches infinity of I equals 1 up to n of m of x of the region Ri, and we sum up to infinite number of regions. And now this subregion mx of this region is going to be equal to, again, mass times by the center of mass. So it's a tendency to rotate about this axis. So what we're going to do is it's going to be from this point all the way across times by mi, and again it has a mi, the mass of that section. So we'll write that down. Mi times by center mass in the y-coordinate, and this equals 2. We've already solved this one. That's just the average length, and again the rho times it by area is the mass, and then that's density, constant density, and then we have this yi, which is 1/2 f of x, like that, plus g of x. And now let's plug in our area. We know this is going to be rho, and then times by the area is, again, the area is just going to be simply delta x times by the difference right here. Actually, yeah, these brackets are a bit off. This has to have something like that and like this. So I'll have to draw a bracket like that because of this delta x multiplying like that. So yeah, that's just to be perfectly correct there. And now this ai, that again, that's going to be delta x times it by a different bracket here. This is going to be f of x I minus g of x I, and then we again multiply by half. Oh yeah, there's a bunch of different brackets, plus g of x I. Let's write this neater. And now what we gotta do is multiply these out. So let's just put the constant stuff out. Delta density constant, and then delta x times 1/2. And now we have to expand this by just foiling it out. So multiply this by that, and then this by this. Yeah, and we're just simply foiling it. So what we'll get is f of x I. Let's write this in a giant bracket like this. So we have f of x I times it by f of x I. That's going to be squared. And then we have to have this f of x I and then g of x I. So plus then g of x I, and now we have to have the g of x I times f of x I. That's going to be negative. There's a negative sign, so we have negative g of x I plus, I'll also write it over here. I'll write the f of x I first because it's the exact same thing, and again it's the conjugate of it, so that cancels. That's why this is the same thing but minus and a plus. That's what definition of conjugate is. Okay, so we have that, and then we, last one, g of x I, and then multiply by g of x I again. So that's going to be squared, and it's a minus. So we have g of x I, let's write this neater. And this is squared, and then finally close bracket. So all we do is this cancels right here. So what we end up getting is rho, and then I'll just put 1/2, and then we have this f of x I, I'll just put the center line above, squared minus g of x g of x like that, I squared, and then put the delta x. Yeah, last time I forgot, but here we just put it like that. So that's for our subregion, and then again we just take the full limit. So the total moment about the x-axis is going to be equal to the limit as n approaches infinity of up to n I equals 1. Again, this is for the subregion, and like I wrote here, it's the summation, it's a limit of this whole summation. So we get now rho 1/2, just plug it in. Close bracket minus and then delta x. And again, this is the Riemann sum. Write this as an integral equals 2 and take this constant out. I'm just take the density out, and from integral from a to b of, and again this becomes infinitely small. Infinitely small is delta x, so this xi is going to be coincide. You're going to have basically a one line rectangle or just a line. So that's going to be our 1/2, and let's write the bracket like that. F of x squared minus g of x squared. It's different brackets because we have so much different brackets right here. And then d of x for infinitely small like that. So what we end up getting now is we have to solve for our center of mass. And again, recall that center of mass in the x direction is simply going to be the moment about the y divided by the total mass, which equals 2 OMY. That's let's just scroll up. That's just this one, x fx minus g of x. So what we get is, and it's rho integral from a to b of f of x fx dx by minus g of x. And then divided by the mass. Again, the mass is going to be rho times by the area of the region. So these just cancel. And then I'll get to the other one right here, and then I'll write it all in the summary. So those cancel. We're just so that's what we have there. So mx. So the y coordinate for the center of mass is this moment about the total moment about the x-axis divided by the mass, which equals 2 rho times area from integral from a to b of 1/2. I like to write the other brackets because that's this one right here. 1/2, and then we have f of x like that squared minus g of x squared dx, and then divided by the mass, which is the density times by the area. And again, these cancel, so thus we have our final formulas, which are x is equal to, the center of mass in x direction is equal to the integral from, I'll just go 1 over a. 1 over a integral, and the densities cancel, so it's not dependent on density. X times fx minus g of x dx. And the y coordinate is 1 over a, the total area, a, b, and again we have to have the 1/2, just put it like that. And then squirrely bracket, just because we have so many brackets, square bracket, regular parentheses, like that. And then this is going to be g of x squared dx. Yeah, and basically, yeah, so this is our center of mass for a region bounded by two curves. Like that. So erase the thus. Oops. Yeah, and just write thus, like that. Yeah, and now where the area is simply going to be, well, again, like I showed in my earlier videos on area, when you have it between two curves, a is equal to the area. In this case, it's going to be equal to integral from a to b of fx minus g of x dx. And you could look at this visually as well, simply just to recap on areas, x, y, Yeah, you can consider it as the full area like this of, let's say, f of x. Y equals fx here as this full area subtracted by the area underneath this one. This is y equals g of x. Yeah, and basically subtract the area underneath this curve like that. Actually, I'll draw it this way just to make it more visible. And then what you end up getting is the top area in between them. So because you're subtracting two areas. And also what's interesting is if we let's say g of x equal to 0. So if this function g of x is equal to 0, then this is simply the x-axis, because basically whatever value of x you put in here, you get the y value of 0. So if we have this case, this is simply the x-axis, and then what we end up getting is this integral from here is integral from, 1 divided by area for the x-coordinate of the center of mass from a to b x times fx minus 0, so that's just cancels out. This is just f of x dx. And likewise for the y-coordinates, 1 over a, integral from a to b of 1/2, and then we end up getting, this is just going to be simply fx squared dx, because the g of x squared is 0. So this is exactly the same as what we had above, and the area is going to be equal to integral from a to b of simply f of x, because g of x is 0. And this is the exact same thing as the above. So in our case, these formulas I just derived are more general. And these are, again, the exact same thing, but where g of x is equal to 0. And this proof is very, very similar to the one I did for this case, except now our hi is different. It's going to be the top, it's going to be above here. And that formula we used to get that center of mass of the rectangle is the average distance from the x-axis. So you have like this. So that's pretty much all that changed. And again, this changes, so the area changes in the formula. So the area is going to be delta x times the difference, like that. And then we end up getting the formula that's slightly different than this. Anyways, that's all for today. Hopefully you'll learn. And like always, you can download these exact notes in the link below. And thanks for watching, and stay tuned for another Math Easy.